Hello everyone. So far we have seen boiling and condensation in the fifth unit. Now the last chapter heat transfer is thermal radiation. This is the third mode of heat transfer, where the heat travels from high temperature to the low temperature, or in the form of electromagnetic waves. The heat travels in the form of electromagnetic waves. It is not high temperature, low temperature. It depends upon the emissive power, absorptivity, some other terms are there that we will see now. In the coming classes, we will see in detail. Now, what is radiation? Radiation heat transfer is the energy transfer or exchange in the form of photons, electromagnetic waves between the bodies of different temperatures. Between the bodies of different temperatures, the heat transfer or energy exchange in the form of electromagnetic waves. You need to remember that point. The heat in the form of electromagnetic waves is radiation, and heat exchange takes place in the form of electromagnetic waves or photons. What are electromagnetic waves? They are the energy packets of photons which has a certain wavelength frequency when they move from one source to the other other body. It requires no medium for transfer of radiation, even in vacuum also. Yes, it is very clear. Even in vacuum, say, the best example is the solar rays that are coming from the sun will get distributed to all the parts of this universe, because it requires no medium. Hence, it requires no medium for the propagation of the waves, light waves. Now, example, electromagnetic waves from sun into the space, yes, and onto the earth requires no medium. And one more example, electric bulbs, heat leakage through walls of thermoflask. It is also one of the example for radiation. From electric bulbs you get radiations we call the visible rays under the frequency of 0.4 to 0.7 micrometers. Sorry, wavelength, not frequency. The wavelength of 0.4 to 0.7 micrometer. The visible rays are under that wavelength category, and we can see these rays. Now, the amount of quantity of radiation depends upon the temperature of the body. Yes, the emissive power of a body is dependent on its temperature, because the emissive power is proportional to the fourth power of its absolute temperature. It is very important to remember the point. As the temperature is higher, increases, the emissive power will also increases, and it also depends upon the emissivity. Example, and some other examples for radiation, we have furnaces, combustion chamber, nuclear explosions. They all come under radiation. So from furnaces, how we get the heat? We feel heat outside. It may be because of radiation. And from the combustion chamber also, we use radiators. And nuclear explosions. So there generally we discuss about the radiation. If any heating source is there, means we can expect all the three different types of modes of heat transfer. Conduction is possible, convection and radiation even is also possible. Depending upon the conditions and constraints, we solve our problems, we do our analysis, and based on that we formulate and we solve the problems. Now, the spectrum of magnetic waves, this is just now we discussed the wavelength of the rays. Different types of rays that is known to mankind is gamma rays, X-rays, ultraviolet rays, visible rays, infrared rays, and microwaves. Either the wavelength, their ranges are shown here in this PDF. 10 to the power of -4 is the maximum. -5 is the maximum range. The minimum is 10 to the power 4 micrometers of the wavelength. When the wavelength is very less, their frequencies are very high. Their inverse wavelength is inversely proportional to the frequency. The wavelength is more. Say for microwaves, the wavelength is more. Its frequency is less compared with that of the gamma rays and X-rays. Now, let us see some important terminology, that is uh, surface emission properties. Surface emission properties like surface temperature, nature of the surface, wavelength or frequency of radiation. Say you have a surface and it got some temperature T, and depending on nature of its surface, the light will get the electromagnetic waves. We should not say light, electromagnetic waves may emit dependent upon its nature, the type of material. Say for black body it is different, white body it is different. Now the total emissive power epsilon, it is an important, and we are going to enter into slowly entering into radiation. Stephen Boltzmann constant with respect to black body. The total amount of radiation emitted by a body per unit area and time is emissive power. Total amount of radiation emitted by a body per unit area and per time is emissive power of a black body. It is indicated with EB, directly proportional to T to the power of 4. Its absolute temperature T should be in kelvins. It is not in degrees, it is in kelvins. Temperature is in kelvins. Now E is equals to, the proportionality constant is removed with sigma, and we call sigma as Stephen Boltzmann constant. And moreover, if we multiply with area, we get sigma A T power 4, then that will be in watts. And sigma is, the value is given, Stephen Boltzmann constant. Sigma is equals to 5.67 into 10 power minus 8, 10 power minus 8 watts per meter square, Kelvin power 4. And we have one experiment in our lab to find out Stephen Boltzmann constant, sigma, 5.67 into 10 power minus 8. So likewise we have some other terminology. Monochromatic spectral power E lambda, the rate of energy radiated per unit area of the surface per unit wavelength, unit area of the surface and per unit wavelength. Monochromatic spectral power E lambda, emissive power is equals to E lambda into D lambda, watts per meter square, integral 0 to infinity. We have these terms to be remembered, can be asked for 2 marks. Next, emission from real surface, that is emissivity. E, the emissive power is equals to epsilon sigma A T power 4. This epsilon is emissivity of the material. The emissivity of the material, for black body it is observed that emissivity is equal to 1. Now what is emissivity? Emissivity is equals to E by EB, the ability of a surface of a body to radiate heat. It is an ability, like it is just like a characteristic, it's a character of a material. The ability of a surface of a body to radiate heat, it varies from 0 to 1. This we have seen in our lab. We did an experiment to find out emissivity of a body and to compare it with a black body. Next, absorptivity, reflectivity, transmissivity. Let us consider a body and some radiation is incident on that body. So what happens to that radiation, that heat in the form of radiation? What happens to that? What happens is some part will get reflected, some part will get transmitted, and some other portion of that radiation, incident radiation, will get absorbed. And it is given with G. Capital G is that incident radiation. G is equals to Ga. Absorptivity is indicated with Ga, plus transmissivity is G tau, plus reflectivity Gr. Now you take G to the right side, we get 1 is equals to Ga by G plus Gr by G plus G tau by G. Ga by G, it is absorptivity. It's a fraction of fraction with 1. The total sum is equals to 1, and we call Ga by G as Ga is incident radiation, Ga is absorbed radiation. G is the total incident radiation, Ga is absorbed radiation, and Ga by G is called as absorptivity. Similarly, reflectivity and transmissivity. The absorbed radiant energy is converted into internal energy. Absorbed, yeah, this point. So whatever the absorbed energy is there, that is in turn converted to the internal energy of the body or the system. So 1 is equals to alpha plus rho plus tau. Alpha absorptivity, rho reflectivity, tau transmissivity. Sum of, it's a bit question. You can ask this. What is the sum of absorptivity, reflectivity, transmittivity? Its value is equals to 1, and it is dependent upon the total radiation G. Now, for a black body, rho is 0, tau is 0. Only the absorption. Whatever the radiation falls on it, it absorbs completely. That is, alpha is equal to 1. For a white body, whatever the radiation falls on it, it completely reflects it. So reflectivity is 1. There is no absorption, there is no transmission. So example for white bodies are gases, hydrogen, oxygen, nitrogen, it is given here, and their mixtures have the transmittivity equal to 1. Next, opaque bodies. Opaque bodies which will not allow the transmissivity. So alpha plus rho is equal to 1. Opaque body just like a body which it is like an obstacle in a flow. So in the heat flow, the opaque body acts as an obstacle. The radiation, it will not allow the radiation to transmit through it. Either it absorbs or it reflects. That's it. So this type of bodies will form thick shadows. No, gray body. Coming to gray body, if alpha plus rho plus tau is equal to 1 and uniform over the entire surface of the body and over entire wavelength of the spectrum, then they are gray bodies. Sum is equal to 1. Alpha plus rho plus tau is equal to 1 and uniform over. So this property is uniform over the entire surface of the body and over entire wavelength of the spectrum. Then such type of bodies are called as gray bodies. Or alpha does not vary. The absorptivity does not vary with temperature and wavelength of the incident radiation. Either whatever the radiation that is falling on it, the alpha absorptivity does not vary. They are called as gray bodies. Next, colored bodies. The absorptivity alpha varies with wavelength of radiation. So different colors will have different absorptive capacities. Green is different, red is different, and black is different. So colored bodies are different. Next, the concept of a black body, pure black body. It is alpha is equals to 1, absorptivity is 1, rho is 0, tau is 0. It emits maximum amount of thermal radiation at all wavelengths at any specified temperature. It emits all type of radiations at any specified temperature. It is a diffuse emitter. Emitted radiation is independent of direction. Yes, the emitted radiation is independent of direction. There is no specified direction that like just like an explosion, just like you have a body, center body, a point body, and that body will emit the radiation in the form of, in all directions it will emit. There is no specified direction that it has to move from one to the other. No, it will emit in all directions. There is no single direction that the radiation has to emit. Next, Stephen Boltzmann law. Stephen Boltzmann law says that, just now we have seen that emissive power of a black body is equals to sigma T power 4 watts per meter square. Sigma is equals to 5.61 into 10 power minus 8. Stephen Boltzmann law. And EB is equals to 5.67 into T by 100 power 4. Yeah, thank you. And we will continue the next session with Kirchhoff law. As of we have discussed about the black body, it absorbs all the radiations. No, under equilibrium conditions, it emits all the radiation. Its emissivity is equal to 1. That we will say absorptivity is equals to emittivity under equilibrium condition. That is Kirchhoff's law. This we will discuss in the next video. Thank you.